So next we are going to talk about the generative adversarial network. I don't think I have time to talk about this video understanding as well as this cloud point cloud. But I can just briefly talk about the different what are the additional things about video understanding and point cloud. So if you think about it, a lot of when we are doing so far, we are all handling like a 2D image, right? So when you have like for a video, you have like 30 some frames per image per second. So when you are trying to understand a video, essentially it's a sequence of continuous images, right? And so there are temporal redundancies. So a lot of video understanding, trying to understand like what's going on during this video, trying to track the a object inside this video, like when it's moving around this frame. So those things are kind of like this segmentation, right? It's a dynamic segmentation. So all those videos, like then like the model essentially, if you just naively apply 2D image algorithms, now you need to apply 30 times per second to do the segmentation, which isn't really efficient, right? So a lot of these video understanding models, what they are trying to do is to explore this temporal redundancy across all these different frames. Okay, so I'm going to upload the slides, and if you are interested, you are welcome to read. There are also a bunch of papers. And also on the other hand, for point cloud, what a point cloud is basically the LiDAR, when it's shooting all these LiDAR out, you get like reflections, right? So you got like a point cloud of all these 3D environment surrounding you. Okay, so what that does is also like compare with the 2D image. Compare with the 2D image now, it's a 3D information. It has X, Y, and Z information. So again, compared to 2D image, now we have another dimension. So again, a lot of optimization techniques are trying to optimize the third dimension. Everything we learned so far, all this quantization, all this sparsity, and all that, they all works for all these 3D models. Okay, so it's just like they have some specific optimization for the third dimension. One for video, it's the time dimension. For the point cloud, it's the Z dimension. Okay, so let me just focusing on the video generation for this for this week. Okay, so oh, this is just what I talked about. So I'm going to mainly cover the first part, again the generative adversarial network, see how it's used to generate images. Okay, so this is if you are not familiar with GAN, I believe most of you probably at least heard of it and know roughly what it is. So generative adversarial network, it's used to learn to generate by an image by adversarial learning. So the model looks something like this. I have a random input. I go through a generator. If you think about what is a generator, usually you can start with a autodecoder, right? So when you have a auto VAE, you have an encoder and a decoder. What a decoder does, essentially, it's decoding from a latent space to a real image, right? So you can starting from there. So the generator can, using a random input from the latent space, you can basically and generating a image. And depending on where you are sampling the input, you got like different inputs, different images, right? Then like when you have this image, you have a discriminator. A discriminator is basically a classifier. See, oh, is this truly a image or not? Or is this truly a image that belongs to my, like human perception of a real image, right? So this is a classification essentially. And then this discriminator can also like do, for example, I can have some real image and I can compare. Oh, is this a fake image similar to real image? Okay, so discriminator can basically discriminate that. And during the training, during the training, there are two losses to optimize. So one, we want to optimize the discriminator. One is we want to optimize the generator. So from the discriminator perspective, what I want to do is that I'm going to tell if it's a real image, I'm going to tell it's a real image. Okay, that's my accuracy, right? Also, if it's a fake image, I'm going to be able to tell it's a fake image. Does that make sense? So that's the loss function for the discriminator. Okay, so basically says, if it's a real image, I'm going to know it's a real image. If it's a fake image, I know it's a fake image. Okay, but from the generator's perspective, what it wants is that I want to generate a realistic image, right? Right? So every time when I'm training the generator, I'm going to freeze the discriminator. Okay? And then I'm going to tune the model, tune the weight of the generator. Essentially says, oh, I want to generate an image so that the discriminator will think the fake image is a real image. So I want to basically maximize the discriminator's error. Does that make sense? So the discriminator wants to minimize both errors, but the generator wants to maximize the discriminator's error when it sees a fake image. Does that make sense? Does that make sense? So in this way, by doing this iteratively, we can adjust the weight of the discriminator as well as the weight of the generator. So until the discriminator cannot differentiate the image from the real image set and the fake image generated by the generator. And then like during the generation, we will just take the generator, right? So we will just take the generator and generate a realistic image. Does that make sense? So by just alternatively enforcing the loss function, and we can get a real good generator. Okay. Example, learning to generate image from minister. Oh, and also then like we don't want the generator to generate just any random image. We want the generator to generate an image what we want, right? So we call a condition. The condition, we don't want any cat. We want a specific cat we want. The condition can be a lot of things. The condition can be like, say, oh, a class label, say generate a cat or generate a dog or, you know, whatever you want. So it can be a class label, or it can be just a text prompt, right? I want to generate an image like this, and that, this. I can also like, as a segmentation map, so you draw a sketch, okay? Just a segment of the cat and as a condition, say, oh, generate an image like this, but with all these details. Okay, this can also be a condition, right? Or you can be like just a very sketchy strokes, okay? Just a couple of strokes instead of like very detailed segmentation. Either way, we want to give the GAN all these conditions and want to generate the specific image we want, okay? So that's that. So basically we want, so here the X is the image, Y is the condition. Okay, so we want to generate, basically we want to train the generator in such a way that while giving the noise, the random input, and give my condition, say, oh, I want whatever condition you want, and I'm going to generate this fake image, right? And then the discriminator should not be able to tell if it's a real image with real description or it's a fake image with fake description. So in such a way, the generator learns how to generate the image corresponding to this description, to this condition. Make sense? Okay, so this is the condition. So this one gives you an example, this GAN. So what it does is that, oh, I just have this sketch to say, this is the part, this is the part. generate a cloud image. Okay, so that one give you this and this. So this one basically says, if I give you the original image, and this is the condition, right? And I want to, based on this image, I want to have a cat on the back, right? So this is a condition. This is newly generated image. Generative image are more expensive than recognition models, sure. So that's why, we need to do GAN compression. So I think we actually talked about this this technique, this distillation, when we talk about distillation. So what essentially it does is that, well, this is the condition, okay? So this these are two horses. We want to generate this is the two horses. We want to generate two zebras just like the horses, right? So that's the condition, that's the image we want, okay? So we have, what we does is that we have a pre-trained generator using the way we just described. And we want to compress, we want to teach a student that's more efficient than the teacher, okay? So we have three losses and we add them together, okay? And let's take a look at what are the three losses. So one is the reconstruction loss. So basically it's right over here. So basically what it says is that, well, if for this original image, I have a corresponding grounded truth, okay? I'm going to calculate the loss function between the difference, this is the L1 not loss, between this and this, right? That's if we have a grounded truth. If we do not have a grounded truth, we are going to compute the difference between this and between this and this. So what did the student generate should be very similar to what the teacher generate. Okay, so that's easy to understand, right? And also we have a GAN loss, which is right here. So that's basically, we want both the teacher and the student. Well, we want the student to be able to fool the discriminator, right? So that's the GAN loss. Make sense? And then we have this distillation loss. So the distillation loss is a summation of all these intermediate feature maps. Okay, so basically we are adding all these together. So what we does, basically we are subtracting the intermediate activation of these feature maps between the student and the teacher. Okay, so you can see that also here we are learning a super student generator. So this is kind of the SuperNet we learned in once for all. Okay, and then you can see that because of we might have different channels, we also have a adapter that's projecting the teacher's representation to the student space. Okay, so then we learn a student SuperNet. Okay, all good so far? And using this. And we are adding the reconstruction loss, the distillation loss, and the GAN loss all together to train the student model. So once we have the student model, because it's a SuperNet, we are going to carve out all these candidate students with different number of channels. Okay, and then we just actually what they did is they did a evolutional selection. So they pick two students and see which one's good, which is bad, and then they do some evolutional exchange the genetic. Basically they are concatenating some of the different components of good networks and trying to select the next batch of good network. Okay, eventually going through a couple of this search process to find the good final student model. Okay, so this is what this GAN compression algorithm does. And finally, going through, this is basically describing the new architecture search process. And then I finally tune the final model a little bit. Okay, so this one gives you, the results comparison. So this is from a sketch, the segmentation to generate image. You can see the difference. So this is pix-to-pix is original without compression model. You can see that, the color is a little bit off, but you have like 11 more than almost 12 times of compression. Okay. And this is the style kind of, this is a cycle again from this to generate to the zebra. This is applying to the GAN, the comparison. So from here, you can see this is from horse to zebra. You can see that it's much faster, and the FID actually reduced. So FID is the confusion index. So the lower the better. Okay, so that's the distillation-based compression for generated for the first neural network. Next, let me talk about this any cost again. So any cost again basically says, oh, okay, so if you are doing image editing, every time you edit this, if you want to resynthesize the whole thing, it's slow, so it's very hard to be interactive. So the motivation is that like in ray tracing pipeline, people get faster preview by reducing the number of sampled rays. Can we do the same for GAN? Right. So basically, we need to train another model to produce similar output at different resolution and different channel numbers. So basically, whenever the discriminate in style GAN, the original, like without any compression, you generated the image, and only the final resolution is fed into the discriminator. Okay, and another way is that what the MSG GAN does is that it's feeding the intermediate images all to its discriminator. So the MSG, the idea of the MSG GAN is that, well, if I can, like each discriminator layer, I can, this green line here, if each discriminator can train a good intermediate results, then, when I'm generating it, I might just have an early exit from the GAN, so I can have like, low quality, but still good image, right? So, but this one, you need to feed every intermediate results into every intermediate layer of the discriminator from the generator. So this is more time consuming, but this one can only ensure the final image is good. It cannot ensure all the intermediate images are good, right? So what the other basically does is doing this sampling-based multi-resolution way of training the generator. So what it does is that it's a sampling. It does not feed all the images. So it just randomly. Sometimes you sample the image to this, and some sample the image to this, and sometimes sample the image to this. So basically, instead of feeding all of them, just you keep randomly sample some of the image to this to try to reduce the training overhead. But in the hope that by just selectively training the model, that we can still learn for these intermediate layers, how do they generate a good enough image? Okay, so that's basically what they did. And you can see that for style GAN, which basically only ensure the last image can fool the discriminator, right? But here, like we are ensure like each layer can fool the discriminator. You can see that if you only like for the early layers, you can still like have something, but not exactly the final results, but still something. Okay, whereas here you don't see anything. So during the training, it's also like a sampling different number of channels. Okay, to train this. And every time, what they did here is that when you are sampling the number of different channels to train, so this is like kind of the channel pruning idea, right? So when you are pruning channel, it's also using this loss function to ensure the intermediate results from here is consistent with the final results. So it's doing the L2 difference. Does that make sense? So to make sure like every time you generate, it's as close as the final results as possible. Okay. They also did some optimization here. So what it does is that, well, every time when I'm sampling the different channels, the number of channel become a vector. So this vector is encoding how many channels I just sampled from the generator. And this vector as a information of how much I sampled, going through this fully connect layer and going through this final transformation with the discriminator. So so this one, they find that this can improve the consistency. So this image basically they shows different channel and different resolution. So for example, this one means that if I only generated the first layer, which only has 128 times 128, and only using 1/4 of the channels, I can still generate a really good image over here. Okay, that's quite impressive. Similarly, this one compares the number of channel and the resolution and number of channels. Okay, so this one kind of like shows you the results. So that's any cost GAN. So the takeaway is that essentially they are trying to make, it's kind of like an early exit idea. They want to make sure the generator, every layer of the generator can give you a good enough image. Also, like for the number of channels, they are sampling different number of channels to ensure like it's pretty much a channel pruning plus the early exit idea for the generator. Okay. Next, this differentiable augmentation for data efficient GAN. So while the first two are more focusing on the computation efficiency of GAN, this one is focusing on the data efficiency. So to train a GAN model, usually you need like a lot of data, which sometimes we might not have. So this paper is trying to address like how to solve the data scarcity problem. If we don't have enough number of data, what do we do? Data is expensive, takes months, even years to collect the data, along with the prohibitive annotation costs, right? So given limited data, the GAN performance heavily deteriorates. This one gives you, not so nice Obama, this cat, these dogs. If you only give, not limited image. So if you only, in the training data set, if you only have 100 images of Obama, that's what you get. If you only have 160 cats, if you only have like around 400 dogs, still like not so good. So this paper basically is trying to address the data efficiency problem. This one says, well, if you keep reducing the training data from 100% to 10%, you can see the FID just keep increasing. So the model basically got more and more confused. Okay. So and also like the discriminator overfits when we only have a limited number of data, which leads to worse generator performance, right? So because now if the discriminator overfits, basically now the discriminator only know how to only the image that it think it's the correct image. I only see 100 dogs, then it only think that these only 100 dogs are dogs. Like any other dogs are not dogs, right? So that's the problem. So this one basically is trying to show that. So the discriminator's training accuracy actually saturates very fast. But when you are using during the training process, but when you are testing the discriminator's accuracy on the validating setting, you see it's actually really bad because of overfitting. So the question is how do I augment the image? So we know that like for data augmentation, there are some standard ways. So you can crop, you can add some Gaussian noises, you can rotate the image, you can zoom in, zoom out the images, right? So those are all standard data augmentations. But why can't we just do this for GAN? Why can't we just augment the data and fed to GAN and that's it? So apparently there are problems. If we just augment the real image, if we only augment the real image, okay? So let's say like we crop some, let's say just crop. We'll just crop out some of the images from the real image, okay? So let's see the GAN training process, what's happening here. In the GAN process, basically, we are doing the augmentation, the transformation for the real image and updating the discriminator. Now, the discriminator basically thinks, oh, those augmented image are real image. Okay? But and the discriminator think all those are real image. And then basically it will make the generator to be generating image more and more similar to the real images, right? So therefore, in this way, the generator will be enforced to learn all those cropping, all those noises, because the discriminator think those are real. So that will forcing the generator to generate images with all these crops, and the discriminator think that's great. Does that make sense? So that's why if you simply do cropping noise, and that's not going to work. If you just cropping all these augment this real image, it's not going to work for GAN training. Okay, make sense? All good. And if you look at this mathematically, the problem is that the discriminator want to tell and forcing the generator to generate similar to the real image. And during the inference process, the generator just learn all that and generating a image, and the discriminator think it's true, it's great, right? So that will give you the wrong image. Well, then you say, oh, what if we augment both real and fake images for the discriminator? So let's see what will happen during this training process. Well, now the discriminator basically is looking at the augmented image and think they are real, okay? And also when the generator generated the image, and also you're applying the same transformation, so now the image, the generator will enforcing the discriminator kind of now can tell if it's real, it's real. If it's fake, it's fake. And the generator can also, it's forcing trying to fool the discriminator, think, oh, that's because if it does doing the same transformation, so eventually it will learn how to generate an image, and after the generate the image, but after the transformation to for the discriminator. Right? It will learn that, which is great. But if you think about it, when what the discriminator learned is to tell the difference between the augmented real image and the augmented fake image. The discriminator did not learn how to tell if it's a real image. The discriminator knows what is a augmented fake image, what is augmented real image. But the discriminator did not learn what is a real image and what is a good fake image. Does that make sense? Does that make sense? Okay. So to fix all these problems, so basically, what we are going to do is that we are going to do the training. We are going to do augmentation for both fake and the real. So the discriminator learns how to tell the transformed images, okay, or the augmented image. During the transformation, and during the update for the generator, we are also, if you compare the difference is this. So when we are updating the discriminator, we have both fake image. If we are updating the generator, we only using the grounded truth. But what's this approach is trying to fix is that while doing the discriminator, we're using transformed, and when we are updating the generator, we are also going to adding this data augmentation in the data path. Okay, so in this way, because the discriminator learned how to tell the augmented fake and augmented real, right? Now, by doing this, the generator is going to learn how to generate a good fake image, and then going to through the augmentation and give the discriminator can still tell that if it's a good image or not, because we are going through the augmentation process. Does that make sense? So in this way, we can forcing the generator to generate a good fake image, not a good faked augmented image. Make sense? So by adding the data augmentation in the generator training process, we can ensure the generator can generate a good fake image, not a good faked transformed image. Because this one essentially the generator is going to learn how to generate a good augmented image. Because what the discriminator learned is to learn how to discriminate the augmented image. If you are using this discriminator to train the generator is still going to generate all these crops because it learned how to generate a good faked augmented image. Does that make sense? So by doing this, so now the generator really learns how to generate a good image. So compare the style GAN and diffusion model. So so when you are even reducing the training data set, this data augmentation, the FID only increase very small amount. Yes.
So basically, are we like even though we provide the augmented in the ground truth we have the augmented image, what we expect the generator to produce non-augmented image, and then we later do the augmentation when we compare between those two.
So let's say let's see the argument. So we only have limited number of real image. That's it, right? So and then we are going to augment the real image, become let's say just cropping. Okay. So in this training process, we know this training is it's this two-pass alternative process, right? We update the discriminator, then update the generator, then update the discriminator, and then it's also false. For the real image, we crop it, okay? And then we generate a fake image and also crop it, okay? Now discriminator basically is comparing these two cropped image and see, oh, are they different? Basically, you are kind of learning how to tell the part that's not being cropped, like the rest of the part, the rest of the image. Can this discriminator tell if they are different? Can I tell the real image is real image, the fake is fake image, even after they both got cropped? That's good. So in this way, we can train the discriminator to discriminate the cropped images, right? And then if you just using that discriminator directly going to train the generator, remember what the discriminator learned is to discriminating cropped images, not the whole image. Now, if you are using that to train the generator will only learn how to generate a cropped image and try to fool the discriminator. Does that make sense? So now, instead of doing that, now we are, in this process, we train this, when we are updating the generator is appended with a cropping function. Okay? Now, what the generator learned is that, how do I generate a good image? And then the cropper is going to crop that out and use that cropped image to fool the discriminator. So in this way, the generator learned is the good image, not a good cropped image. Make sense? Okay. So all good. Okay. So you can see that this significantly improved the performance for the GAN. Right. So that's GAN. And I'm going to stop here because I'm going to skip the video understanding as well the point cloud. As I said, those are some additional optimization. It's very basically, as I said, whatever we learn for 2D image, they all works for 3D image. It's just additional dimension of optimization. If you are interested, go look them. So far, whatever we learned, you can see that when we are optimizing this, most of them we are trying to find the redundancy, right? We are trying to find what is not necessary, right? Based on some specific optimization. So similarly for 3D, for the dimension, they also for time, I find that most of the images in the video, they are redundant. They are similar to each other. For point cloud, you can see for example, when I'm looking at this here, when I'm trying to understand what's happening with this room, I can see that most of the time, most of the seats are empty. I don't really need to understand what's the empty seats. I only need to understand those spots with students. Right? So those are the sparsity idea in the 3D dimension. So those are kind of those algorithms are trying to take advantage of those observation and propose algorithm to handle those observations. Okay. All right. So let's stop here for a bit and let's come back at let's say 7:10.